There was a request for me to solve an example of a muscle and bone equilibrium problem. So I'm going to go over this one in the video. We did this one in lecture, but you might not be able to make sense of it just from looking at the notes. So let me walk through it. So here's the situation. This is an arm. It's sticking out, and it has some weight that's acting downward. And we're told that the mass of the arm is 3.1 kilograms. And the weight is acting downward at the very center of the arm. So we can take this part right here to be the center of gravity of the arm. So it's halfway through the entire length of the arm. That's the force of weight. We also have another thing that's acting on it, which is the force of the muscle. So this is the deltoid muscle that holds the arm upright when it's out horizontally. So it pulls it up. And we're told that this attaches to the bone 0.12 meters away from the joint, okay? So that's the distance at which this muscle attaches, and it pulls up in this direction at 15 degrees. We're also told that the joint, basically there's some sort of cup here, and that cup pushes out on the bone, and it pushes out in this direction, roughly speaking. We'll call that the force of the joint, and it's pushing out at some angle alpha. And our task is to figure out what's the force of the muscle, what's the force of the joint, and what is that angle alpha. And we're told that the entire system is in equilibrium. So if the whole system is in equilibrium, we know we've got these types of equations. The sum of the forces in the x must equal 0. The sum of the forces in the y must equal 0. And the sum of the torques must equal 0. So you can take a look at this and figure out which one of these equations might work best for you. And it turns out that probably the best way to go is with the torque equation at the beginning. And I'll tell you why. So if I look at this situation with the arm, I've got X forces coming from the force of the joint, right? I've got some component of that that's pushing that way. I've also got some component from the force of the muscle that's pushing that way. And I don't have these things solved yet, so I can't really resolve the whole thing in X. Likewise, there's a component of this force that's in the Y direction. There's a component of this force that's in the Y. And I do know that, but because the force of the joint and the force of the muscle are unknown, I can't really solve the forces in the Y. Let's try this, the sum of the torques. So I think that might be a little bit easier. So I'm going to draw a simplified version of it. So let's say this is the pivot point. We've got something that goes out like this. We've got mg pointing down. This is the force of weight. And right here, we've got something that's pulling up like that. And that's the force of the muscle. Now, if I can sum the torques around this point here, then basically I would have an equation that only involves one unknown in some way. Because I do know mg. I'm told the mass of the arm is 3.1 kilograms. And I know g, okay? So I can basically solve that right there. So 3.1 kilograms times 9.8 meters per second squared. I can calculate this, 9.8 times 3.1, and I get 30.38 newtons, pointing down, all right? Now, I don't know the force of the muscle, but I do know the angle at which it's acting. It's acting at 15 degrees. So if I want to sum the torques, what I can do is I can take the torque that's caused by the muscle, and we'll take it like this. I'm just going to draw this right here. Okay, so here's the torque caused by the muscle. And what I want is I want that component of the force that's acting perpendicular to the distance. Okay? So what I want to do is I want to take this component here, which is going to be the force of the muscle times the sine of 15 degrees. That'll be that component there. It would also be that component there, okay? And we know that this is 15 degrees right here. All right, so I'm going to take that component, and I'm going to multiply it by the distance. We're told that this distance is 0.12 meters, okay? And I know that this is going in this direction, which is counterclockwise, so it's positive. So here's this torque from the muscle. Torque from the muscle is a positive one. And I'm going to take 0.12 meters times the force of the muscle times sine 15 degrees. So I've got that. On the other hand, I have this torque that's caused by the weight of the arm. It goes down like this. As we calculated before, it's 30.38 newtons, like that. And the distance we're told here is 0.24 meters. Okay? So the torque due to the weight is going to be rotating in this direction, which is clockwise, which means it's negative. This is going to be negative 0.24 meters times 30.38 newtons. And the sum of these two torques should equal 0. So I'm going to write that down. 0 equals 0.12 times the force of the muscle times sine 15 degrees. That was our first torque caused by the deltoid muscle, minus 0.24 times 30.38 newtons. I have that. I can try to solve this so that I can isolate the force of the muscle. So I'm going to bring this to the other side. I get 0.24 times 30.38, and that's going to equal 0.12 force of the muscle times sine 15 degrees. Force of the muscle will then be 0.24 times 30.38, and this is going to be newtons, and this is going to be meters, okay? Divided by 0.12 meters times sine of 15 degrees, okay? And I'll just punch these things in, and I get 0.24 times 30.38 equals 7.29 Newton meters. And down below, I have sine 15, so 15 degrees, take the sine of that, and multiply it by 0.12. And then I get 0.03, and this is in meters. So I cancel the meters, and I divide this by, and then I get 235 newtons. And there I solve for the force of the muscle. So I can go all the way back here and say the force of this muscle has got to be 235, like that. And I know the angle of it. So now that I've dealt with the sum of the torques has to equal 0, what I can do is tackle one of these other problems, whether it's this one or this one. So it doesn't really matter which one you go for. Let's just try it, okay? So let me copy this arm and put it on the next page so we can work from that. Okay, here we go. So now what I'm looking for is, let's just say I'm going to do the sum of the forces in the, let's say, y direction equals 0, okay? And I know from before that this thing pointing down was 30.38 newtons. And we just solve for the force of the muscle, and that's 235 newtons. So I can just say 235 newtons. 235 newtons there is the force of the muscle pointing in that direction. So now I want to look at the y components of these things. All right, so I'm going to draw a simplified diagram. I've got the force of the muscle going this way, and I've got a y component for it like that. All right, and then I've got, the joint is here. So this is the arm going out like this. I've got this guy going down with 30.38 newtons, and it's purely y. It only goes in the y direction. That's in the y direction. And then the force of the joint, I don't know what that is exactly, but I know it's going to have some kind of y component going down. So I'm going to call this the force of the joint in y. This is the force of the muscle in y. Okay? And what I'm claiming is that the force of the muscle in y, which is a positive force because it's going up, minus the force of the joint in y, which is negative because it's going down, minus 30.38 newtons, which is the weight of the arm, and that's going down. It's negative. All this equals 0. All right? So I do know, or should be able to find out really quickly, the force of the muscle in y. So if we go back up here, remember, when we were looking at the force of the muscle, we wanted to calculate its y component when we took the torque. That was this part right here. Okay, so the force of the muscle times sine 15. So I can calculate that. The force of the muscle is 235. So the force of the muscle in y is 235 newtons times the sine of 15 degrees, okay? That is just this guy, okay? Minus the force of the joint in Y, minus 30.38 newtons. You got that? Let me calculate this guy. So 235 sine of 15, I've done this before, times 235 is about 60.8. So 60.8 newtons minus 30.38 newtons minus the force of the joint in Y should all equal 0. So let's calculate this stuff and bring it to the other side. Okay, so this guy minus 30.38 equals 30.4, and I'm going to bring that over, and 30.44 newtons approximately. So it's going to be positive. I bring it to the other side. It's going to be like this. And then this is the force of the joint in Y. So that's useful. That tells me something. I don't have everything solved, but I do now have this component that's going down this way. That's the force of the joint in Y. So that's helpful. And I can basically stay with that. If I can now get the force of the joint in X, then I will fully know the force of the joint, because I'll have its Y component and then I'll also have its X component. And once I have that, I'll be able to get what the hypotenuse is. So let's go to the next equation. We just solved things in Y. Now we're going to solve the sum of the forces in X should equal 0. And for this, here's my simplified diagram. So here's the arm going out. I don't have to worry about the weight going down. That's only in Y. What I have here is something like this. This is the force of the muscle, and it's going to have a component going this way. So this is the force of the muscle in X, going like that. And then the joint goes something like this. I don't know exactly what it is, but it's going to have a component that goes like that. And that's going to be the force of the joint in X. And those guys must be equal. There is no component in the X direction caused by the weight pulling down. So I know that this must be true. The force of the muscle in X must equal the force of the joint in X, at least in magnitude. They're going to point in opposite directions, obviously, but we can figure this out. I can figure out the force of the muscle in X. Let's go back to what it looks like. So this is the arm, and that's the force of weight. And remember, this guy is pointing like that, so that's the force of the muscle. And the force of the muscle, we said earlier, is 235 newtons. And we know it's at 15 degrees. Okay, so I can do this. 235 newtons. This is 15 degrees. And I want this component right here. All right? So the way we get that is basically I say I can draw a triangle like this. Not a great triangle, but let's say it's something like this. I know the hypotenuse is 235 and newtons. And what I want is this side right here. And this is the force of the muscle in X. And since this is the adjacent side, I can say cosine of 15 degrees times 235 newtons should equal the force of the muscle in X. Let me plug that in, and I should have 15 degrees cosine times 235, and it equals about 227 newtons. That's the force of the muscle in X, like that. Now, because we set it up here saying the force of the muscle in X must equal the force of J, the joint in X, we know that the force of the joint in X has got to be the opposite of that, minus 227 newtons, like that. So let's draw the overall diagram, and we'll put the forces in. So this is the weight. It's 30.38 newtons, like that. This is going to be the muscle. It's acting like this way, and that's 227 newtons, like that. And it's acting upward like this. This is the force of the muscle in Y. So let me get that. That's going to be 60. So this is the force of the muscle in Y. That's going to be this, which is going to be this, 60.8. So that's 60.8 newtons, like that. The force of the joint is, oh, and let me just draw, this is what the force of the muscle is going to look like. It's like that. And the force of the joint is going to look something like this. And I'll reserve black for the components. This guy must have a component going that way, which is 227 newtons. It's got to be that. And now it's got to have a downward component, something that goes like this, all right? And that downward component, the force of the muscle in Y, force of the joint. Let me erase that. Force of the joint, sorry, mistake on that. Force of the joint in Y. That whole thing is the force of the joint. And what I'm after now is the force of the joint in Y, which is just this guy, like that. And we calculated that before, and the force of the joint in Y is 30.44 newtons, something like this, minus 30.44 newtons, like that. So now you can see if I add everything up, if I just look at the x's, so 227 going that way, 227 going that way. It's the component of the muscle in the x direction pointed to the left, component of the joint going that way to the right. These guys cancel. And then in terms of the y, I've got something like this, 60 going up, roughly 30 going down, roughly 30 going down. So those guys are going to cancel. Everything works. The last thing we want is what's the angle of the force of the joint. So let me go back to this, and let's draw it down here. Looks like this. So here's the arm, and here's the force of the joint. It goes off like that. And we know a couple things about the force of the joint. We know that this component in the x is 227 newtons, like that. It's going off in that direction. And we know that this component going down like that is going to be 30.44 newtons, like that. Okay? So now I can draw a triangle, and I can basically label the sides. All right? I can say that this is 30.44. I can say that this is 227 newtons like that. The hypotenuse then, which is this guy, should be 227 quantity squared plus 30.44 quantity squared. Take the square root of those things. So let me go ahead and do that. 227 quantity squared, 51529 plus, and this guy is 30.44 quantity squared, 27 roughly. I'm going to add these guys together. 51529 equals, and then take the square root of it, and I get 229 newtons. All right? So the hypotenuse is 229 newtons. It's very close to the length of this longest side there of the perpendicular side, so it's close to that. So 229 newtons. I can also get the angle from it, right? Because now I have all the sides of the triangle. I want to know what this angle, let's call it alpha, 30 newtons roughly, 227 newtons there, and the hypotenuse 229. So I can basically say the tangent of alpha is equal to the opposite, this is the opposite side, over the adjacent, which is this, should equal 30 over 227, or I can say the arctangent of 30 over 227 is going to give me alpha, and if I plug that in, 30 divided by 227 equals 0.13, and I take the arctangent of that, I get something around 7.5 degrees. So that should be about what it is. And let me just check here, go through all this. Yeah, that's pretty close. So that's how you solve this bone problem. I'd say this is a pretty complicated one. It's got a lot of steps in it. And yeah, several pages here. Hopefully this was helpful. Again, I covered this in the notes. This is lecture 26, but this video can walk you through exactly how it was done. And again, just to review, what you want to do is remember it's in equilibrium, and if it is, it's got to obey these three equations right here. It's easier to start with the torque equation because if you do the torque around this location here, you don't have to worry about the force of the joint. The force of the joint is acting at that very point, so its distance is zero. Torque is a force times a distance, but this force of the joint has zero distance from this point, so it exerts no torque whatsoever. And that simplifies things, which allows you to just deal with the force of weight and the force of muscle in the torque equation, which then lets you get the force of the muscle. Once you get the force of the muscle, then you can get the X and Y components, and then you can say that they must match with X and Y of the force of the joint, taking into account this as well. Hopefully that was helpful. Please feel free to leave comments and let me know how I can improve. Thanks.